All right, we're ready for the beginning of the last unit, as sad as that is. So this is not on the test this week. So we're starting electricity, and the good news is we're starting electricity right where we left off in electrostatics. We're starting with electric potential difference, in other words, voltage. Okay? Now, in this unit, when we tend to talk about voltage, it has to do with current flowing, and it comes from a battery. The very first battery that we know of, a guy named Alexander Volta made, and probably why the unit is called after him. And what he did was he alternated pieces of silver and zinc. Silver and zinc, I'm pretty sure it was. And this in between was like wet paper, probably like paper towel. So silver, zinc, silver, zinc. And when he did that, then when he took a wire and he placed it from one to the other, he noticed that a current would flow. He realized that he had created a potential difference between these two objects, between these two ends. And that's exactly what a battery does. Now, for us, we don't tend to draw batteries like that. We draw them with a long line, a short line, a long line, a short line. How many sets of them I put usually just depends on how bored I am. Okay? The short line is always the negative end, the long line always the positive. A way to remember it is to think, well, if you took the plus sign apart and put it end to end, you would get a longer piece than just the negative. Okay? So what we know, if we hook this up to a wire that has electrons in it, when the electrons will come to the positive end because they like the positive end, and then the battery has to do work on those electrons to get them up to this end, right? So if you think about work done on a charge, okay, well, if we go back to the last equations we were doing in the last unit, we're, uh, um, it was V equals EQ over Q, or delta V is equal to delta EQ over Q. So W is the work done. I'm going to put an equal sign there, right? And so really then delta V is equal to W over Q. So work done on a charge is going to be equal to the change in the potential energy that charge experiences times however big that charge is. That's going to be equal to the work done or the change in energy. Okay? In this unit then, whenever we talk about a battery, we really, and what in a real life, what battery does is work on a charged particle, moving it from one side of the battery to the other, so that when it gets to this part, it has electric potential energy, and it's released from the battery, and it immediately turns around and flows to get to a point of lower potential this side, where battery has to do work again to move it across. Because the battery's doing work, it's using up its own energy, usually chemical energy, that's produced inside the battery because of a chemical reaction. And when that happens enough, eventually the battery dies. If it's just an old battery that's not rechargeable, you got to chuck it out. If it's rechargeable, then you plug it into an electrical socket and you give it electric energy to reverse the chemical reaction that's happening inside. If you've been in chemistry, you know lots of reactions are reversible, but one way is usually spontaneous. So inside a battery, whatever these reactants are, right, they're going spontaneously to the products. But once all the reactants are used up, then the battery is either dead or we feed energy into this side and we force the reaction back. If you did take chemistry, you know that we can never get all these back into the reactants. And that's why the more times you recharge a battery, like your phone, each time you do it, you lose a little bit of its life because there's a little more of the products that we can't get back into the reactants. Okay? So one of the equations then that we will use in this unit right at the beginning is V is equal to, well, I guess technically it's delta V is equal to delta EQ over Q, but mostly we write it as V is equal to EQ over Q, or V is equal to W over Q. So they'll talk about the work done by the battery here. Okay, so that's the first one. And the questions that I want you to do with this are on page 692, numbers 1 to 3. Okay, so they will be due to the day after the test. If the test is tomorrow, they'll be due Thursday. If the test is Thursday, they're due tomorrow. I think we could still do the test tomorrow. Okay, the second thing we need to talk about is current. Oh, one more thing up here. We can measure the potential difference of a circuit by something that's called a voltmeter. Its symbol in the circuit is a circle with a capital V, and it does what its name implies. It measures the voltage between 2 points in a circuit, so it's known as a voltmeter. All right, current. You would have seen current in grade 9 science as well. Current symbol is usually a capital I. Now and again you'll see a small lowercase I, but it's usually a capital I. And it's simply the amount of charge flowing by a particular point at a particular time. And I do have notes for you on this stuff. So if you just listen, maybe write down the equations and stuff, but I'll give you notes tomorrow. Okay, so the amount of charge going by in a period of time. That actually tells us the equation, because it's how much charge over a period of time. So Q over delta T. Units then would be coulombs per second. And that is what is known as an ampere. We don't tend to say ampere. We tend to say amps. Okay? And its abbreviation is a capital A, but it is amps. Okay? So 2 equations, but one of them you already knew. Okay? And then the third equation that we'll use in this set of homework is the one that we did from last unit. Number of elementary charges is equal to Q total over the charge of 1. And again, I think I said before, your textbook uses the capital N for it, but it's the same thing. Okay, maybe one last thing on current, and that is that often back in the olden days, people used to think it was electric charge, or excuse me, a negative charge that was flowing. They assumed that negative charge, no, take it back. In the olden days, they assumed it was positive charge flowing. They assumed, just like, you know, planets would move in circles, and if you wrote with your left hand, you were possessed, that obviously it would be positive charge that was flowing in these wires to create current. By the time they had figured out it was negative charge, they had already defined the field by the use of a positive charge. They had been using a positive charge for so long that they were like, oh no. And they figured it out when they isolated the electron. So we're talking like 1908. And so then they had to say, okay, what are we going to do? Are we going to go back and change the way we defined an electric field? Are we going to go back and try to fix this? And they made the only decision they felt that they could. They decided, no, we just won't tell anyone. Well, it didn't really, once people figured out the structure of an atom and that the electrons were in the outside edge and the protons were stuck inside the nucleus, it didn't take long for anybody that didn't need a PhD in physics to say, so how are these positive charges flowing if they're stuck inside the nucleus? And so you will hear even today people talk about conventional current, and electricians tend to use conventional current, meaning they tend to think of charge as being positive, charge flowing. But physicists and lots of engineers use electron current because that's really what it is. It's really negative charge flowing. In the end, it doesn't make any difference in the math. Okay, I will usually use electron, and because of that, I will show my current flowing from the negative end of the battery. You will sometimes notice the book has it coming out of the positive end. That means they're using conventional. Math doesn't change at all. There are 2 more pages for homework questions